Thank you, ladies and gentlemen. This time is to be honored. I want to present our paper in the title Disturbance Storm Time Index Prediction using Long Short-Term Memory Machine Learning. My name is Wihayati. The second writer, Mr. Hindriyanto Dwi Purnomo. The third writer is Mr. Surya Satria Trihandaro. We are from Department of Information Technology, Satya Wacana Christian University, Salatiga, Central Java. The contents our presentation is the introduction, related works, research methodology, results and discussion, and the last is the conclusion. The introduction, our research, we want to raise the phenomena that is not uncommon, that is uncommon in our country. Its issues is about the space weather that was the phenomena of geomagnetic storm. We know that the geomagnetic storm is the regression of corona's Hall's result in plasma flow that will hit the Earth's magnetosphere at periodic intervals and cause recurrent geomagnetic storms. This impact is actually there are so many disrupting human activities on Earth and in outer space. So the scientists in physics and various fields attempts to define the relationship between solar wind phenomena in interplanetary space and geomagnetic index over the past few decades. And then as in the engineering of computer, we want to examine about the how to measure the accurate quantitative short-range prediction of space weather has recently become increasingly important because of the expanded level of human activities at high latitudes and space. Now, the field in space weather, in this case, becomes visible as an object of scientific disciplines involving academia and industry. The opportunity is quite challenging in creating a space weather prediction model that can answer problems in real time based on physics forecast and data analysis. So we can propose time series analysis because it's very helpful and they do not require a complete understanding of the physical processes involved in the interaction between the solar wind and the magnetosphere. Now I want to explain the related work. And nowadays, the DST index prediction has been carried out using the neural network. It begins in the early of 2000. This method we know as artificial intelligence approach to observe the DST index effect on the solar wind. Then it developed more in-depth prediction with a recurrent neural network method during geomagnetic activity periods, mainly when storms occur. In nowadays, the present study design RNN to predict the DST index based on the interplanetary data and the solar wind data. It combines RNN, PCO, and genetic algorithm and modeling in the DST index prediction, particle swarm optimization in this. Now, some authors also focus on predicting DST index 1 hour ahead using ReMF components. It's so physically it has been done by the Xu and friends in 2020. This research is more in the field of proton density, plasma speed, and plasma flow pressure predicting of DST index. In this research, our paper want to model the DST index prediction using the LSTM model. The data used comes from the NASA OmniWeb. This is a data set we open source for even throughout 2020. A variation of the LSTM network models were employed in obtaining accurate result from the modeling in this paper. Here is the research methodology. We have the distribution of time series data of GST index, and this table is the description with the range value, and we also describe this data with the histogram of GST index data set. In this picture, we know that the skew data is negative 1.008977 and so on. A little about the LSTM network. We know that LSTM is another model of time or processing model. And for the recurrent neural network model, we choose the LSTM method because it's suitable for prediction based on the time series data by modeling large number nested network and complex problems in machine learning. We know that the LSTM contains more compute than RN because it uses a sigmoid function and the hyperbolic tangent function. This sigmoid function is a function that transforms value between -1 and +1 into values between 0 and 1. Next, we also use the optimizer to prediction the model. And this paper also employs an optimization algorithm to optimize the gradient in the prediction model. The optimizer that we use is adaptive moment estimation optimization, as we call ADAM. This is the pseudocode of the algorithm of ADAM optimizer. And to evaluate the LSTM model, we use the RMS equation for model testing. Here is the result and discussion. We have the output, model output validation, and we have the distribution of real, training, and the prediction. We describe it in a different color. This is the graphic of real training and prediction data of the DST index. As the training and testing, we have two scenarios. That is, we divide the prediction with the DST index data set, and for the first, we split into 70 as the training, and 70% in the training and 30% for testing. And the second, we have divide the data become 80% and 20 for testing. And the number of LSTM, we use 5 blocks, 10 blocks, and 20 blocks, and which is in epoch number we employed in for variation 5, 10, 20, and 50. Here is the result. And from the result, we know that the experiments has made two comparison model for training and testing data from the dataset. And actually, the difference in RMSA result for each test is not so significant. In the difference, we call minimal. And now we call that this paper has implemented a simulation test index precision for in the year 2002. And for the future work of this research is we suggest to predict the DST index using several parameters obtained from the solar winds and electromagnetic fields dataset.